Hello all. Today we're talking about pulsars. Pulsars are incredibly dense dead stars, specifically a type of neutron star. They spin very fast, sometimes as quick as 700 times in a single second, and shoot jets of high energy EM radiation out into space. They are the dead corpse left behind by very large stars that have gone supernova. But why do pulsars spin so quickly? Well, half of the reason is that they're incredibly small. That is, small compared to ordinary stars. Our own sun is around 1.4 million kilometers across, whereas a typical neutron star has a diameter of about 20 kilometers, which is about 1/5 of the size of Greater London. The second half of the reason pulsars spin so quickly is that despite their small size, they carry about the same amount of angular momentum as the star's core that formed them. Let's talk about angular momentum. Angular momentum is, as you may have figured out from the name, the rotational version of ordinary linear momentum. We know about ordinary linear momentum that the more of it something has, the harder it is to stop it moving. Angular momentum is much the same. The more of it an object has while it's spinning, the harder it is for us to stop it spinning. One thing we know about ordinary linear momentum is that it's conserved. If two objects bash into each other, the total sum of the momentum before they collide is equal to the total sum of the momentum after they collide, assuming there are no external forces acting or anything like that. The same is true of angular momentum. If we think about a blob of matter spinning around in space, as long as there are no external moments acting on it, its angular momentum will stay the same, regardless of whether it expands or shrinks or whatever. In order to talk about the angular momentum of a star, which is a very nearly spherical object, we'll need to build up from the bottom upwards. First, we'll talk about the angular momentum of a single particle undergoing circular motion, then we'll use that to figure out the angular momentum of a 2D plane, and from that we'll work out the angular momentum of 3D objects, like spheres or stars. We define the magnitude of the angular momentum of this particle as being the product of its distance from the rotation axis with the magnitude of its linear momentum. Deriving this result explicitly and really getting to grips with angular momentum requires us to know a little bit about vector algebra, and in particular vector cross products. But we're not interested in that right now, so we'll carry on having taken this result as a given. Now suppose we want to work out the angular momentum of a 2D plane rotating about an axis that cuts the plane perpendicularly. Well, a plane is really just many small particles stuck together, so to define the angular momentum of a plane, we can just add up the angular momentum of all the tiny pieces that make up that plane. Now, we have a sum over these small masses delta m, that are the masses of these little pieces of the plane. However, we would like our expression to be true for a plane that is made out of a single, smooth piece, not a jagged mosaic of these little delta m's. To achieve this, we turn delta m into dm, a differential, meaning the little pieces we've divided our plane into become infinitesimally small. Now we know from calculus that a sum of infinitesimally small things has a special name, an integral. This lets us replace the sum over all particles with an integration over the entire mass of the plane. This is something we will come back to later. Onwards now to a 3D blob of matter. Just as we described a plane as being the sum of infinitesimally small pieces of matter, we can describe a 3D object as a sum of infinitesimally thin slices of matter. In other words, planes. So let's put this into practice and find the angular momentum of a spinning sphere. First, let's work out the angular momentum of a thin circular ring. We think of this ring as the sum of infinitesimally thin segments, which we denote by the angle d theta. Each one of these tiny segments has an angular momentum given by dm times vr, which using v equals omega r is equal to dm times omega r squared. The mass of each one of these tiny segments is given by its density times by the volume of the segment, which is equal to rho times the height of the segment times this area dA on the top of the segment. And this area dA is given by r theta multiplied by the width of the ring, which is dr. If we combine these two expressions, we find that the angular momentum of one of these small segments of the ring is given by rho omega h delta r cubed d theta. As before, we now want to sum up each of these small segments to complete the ring. Because we're summing over infinitesimally thin angular segments of the ring, the summation of the d thetas turns into an integration with respect to theta. Integrating over the entire ring between 0 and 2 pi, we find the angular momentum of the ring to be 2 pi rho omega r cubed delta r h. Next, we can work out the angular momentum of a solid circular disk. We do this by summing the angular momenta of the infinitesimally thin rings from before that make up the disk. We take the ring thickness delta r to become infinitesimally small as dr and sum over the rings. As before, this summation turns into an integration. So we integrate the angular momentum of the ring between r equals 0 and r equals big R, where big R is the radius of the solid disk. This leaves us with the angular momentum of a circular disk being 1/2 pi rho r to the 4th omega h. Finally, we have to break the sphere up into infinitesimally tall disks. The radius of one of these stacked disks will depend on how high above or below the centre of the sphere it is. Specifically, a disk a height x away from the middle of the sphere will have a radius little r, given by this expression that comes simply from Pythagoras' theorem, where big R is now the radius of the entire sphere. Replacing the disk height from before with delta x, where delta x is infinitesimally small, we sum over these thin disks that make up the sphere. So here is the sum over the disks, and as delta x goes to 0, this sum becomes an integral. Now we have to sub in for little r, as little r will in general depend on x in the way that we have just found above. So we sub in for r using r squared is equal to big R squared minus x squared, and we integrate between minus r at the bottom of the sphere up to positive r at the top of the sphere. Going through a few lines of algebra needed to figure out this integral, we arrive at the final result. The angular momentum of the sphere is equal to 8/15 pi rho omega r to the 5th power. But we want to write this in terms of the total mass of the sphere, not its density. By taking out a factor of 4/3 pi r cubed rho, we find the angular momentum of the sphere of radius r and total mass m, rotating at an angular speed of omega, is given by 2/5 mr squared omega. A pulsar, or more generally a neutron star, is formed when a sun at least 8 times more massive than our own sun goes supernova. The star effectively explodes, leaving behind a dense collapsed core. The core shrinks, but the angular momentum stays the same. So before the core has collapsed, it has radius big R, mass big M, and angular speed omega 1. Then after the core has collapsed, it still has the same mass of the core big M, but a smaller radius little r, and a different angular speed omega 2. The total angular momentum before is given by this expression, and the total angular momentum after the collapse is given by this expression. But because angular momentum is conserved, the angular momentum before the core has collapsed is the same as the angular momentum after the core has collapsed. By equating these two expressions, we find this expression for the rotational speed of the collapsed core after it has shrunken down. So let's say the core collapses to a 50th of its original size. That means that omega 2, the angular speed of the pulsar, will be 2,500 times the angular speed of the star before the supernova and core collapse, which is quite a lot faster. Okay, so pulsars spin very quickly, but why are they called pulsars? Well, originally they weren't. In 1967, astronomers Jocelyn Bell Burnell and Anthony Hewish noticed perfectly regular patterns of radio waves coming from the same point in the sky. At first, the source of these emissions was unknown. The radio source was nicknamed LGM-1, short for Little Green Men. They didn't seriously think that this radio source was of extraterrestrial origin, but on the other hand, they had no evidence of what it could be naturally occurring in nature. The jets of radiation emitted by pulsars are directed along the magnetic axis of the pulsar, which doesn't always line up with the rotation axis. If the magnetic axis is offset, the beam of radio waves will trace out the shape of a cone in space. The Earth, with our ground-based telescopes, just happened to sit in the path of a beam from such a pulsar. As the pulsar completes a rotation, the beam of radio waves is momentarily directed our way, so we record a pulse when our radio telescope is pointing towards the object, hence the name, pulsar. Pulsars are really quite mysterious objects. We don't yet fully understand the mechanism that produces these beams of radio waves. There's also a confusion about the size of neutron stars. We don't even know the equation that links the radius of a neutron star to its mass. A lot more is waiting to be discovered. Beyond even pulsars and neutron stars, there may exist even more exotic dead stars dreamt up by theorists. Quark stars, strange stars, electro-weak stars, and who knows what else. The universe is a very big and very strange place. Even today, we are only just beginning to understand the depths of that strangeness. Thanks a lot for watching. If you liked this video, be sure to like and subscribe, and you should also take a look at my website, cosmicconundra.com, and also follow me on Twitter for updates. I've also put a download link in the description that has the notes I was going through when I derived the angular momentum of a sphere, in case anybody wants to go through them a little bit more slowly. Thanks again, and speak to you all soon.